Hi everyone, welcome back to our video lecture series and video tutorial series. In today's video, what we're going to look at is tools for analyzing and getting geometry out of surfaces and curves. And in order to do that, we're going to learn some analysis tools for curves and surfaces. So let's jump in. So what I have here is one of the definitions that we did on the previous module, on the previous unit of the course. I basically have directrix curve, which is this one, which is controlled with this graph mapper. And I have a generatrix curve, which is controlled with this other graph mapper. So anyways, so that's what we have. And we've got just a bunch of things over there. Okay, so there's the translation surface, and this can be a loft surface or any kind of surface. So let's look at the first thing that we're going to look at is how to analyze curves and how to get sort of different geometries out of curves. So if I go to curve and I go to analysis, I can go to evaluate curve. And this little thing right here, this little drawing, it has like the drawing of a curve, a point that lies on the curve, some sort of arrow that represents a vector, and the T right here, right? So that's what it like. That's the symbol, and it talks about a bunch about what this thing does. So if I, for example, if I plug in the curve here, and it asks for a parameter here, and in this case, a parameter is just a distance that you can walk along the curve. So imagine that this is a piece of string that lies exactly along the curve. So you have the curve and you have the point along the curve. So imagine that you're a little ant that's walking, a little insect. You're a very small insect and you're walking along the curve. So if you're walking along the curve, the distance that you walk along the curve, that would be the distance that you've traversed from the start of the curve to wherever you're at. That would be your parameter or parameter here. And it's a little bit different than the concept of parameters in Grasshopper, although it's pretty close to that. So for example, if I'm over here, let's just say that I'm a little insect and I've walked 10 units, right? So this point right here, that would be parameter T equals 10. Could be 10 meters, 10 millimeters, 10 inches, whatever. And then if I go all the way up to here, maybe let's just say that this is parameter 20 units. So what that means is that you've walked those many units along the curve. So let's look at what that looks like here. So let's just grab a slider and plug it into the parameter input of this component. So right now, if I'm here at 0, you can see that the point is here at t equals 0. If I move this slider over here, you can see that that point is t equals 1. And if I continue moving or increasing this slider by just increasing that range there, for example, let's just put it on 5. So you have here parameter t equals 5. Okay? So what that means is that this point here will be that point, and it'll have its x, y, and z coordinates, right? That you can just look at it by getting a panel and connecting that output. So it has its own coordinates for that, okay? And it also gives you another kind of component right here, which is tangent, which is the tangent vector of the curve, or the vector tangent to the curve at that particular point. So so that's another output that you get, and so you get my meaning, right? You get what it's doing, and eventually, if you walk along the curve, you keep walking along the curve, and eventually you'll basically go outside the curve, and Rhino and Grasshopper will no longer know what to do with that number. Basically, what that means is that this point right here, or this parameter, it's what it's called is basically parameter is outside the curve domain. So it's saying parameter is outside the curve domain. So what that means is that I tried to supply a number here that was outside of the curve domain, and the curve domain is nothing else than its length. I can actually get a curve analysis length, and I can just plug that curve there, and I can see that the curve length is 35.45. So if I put this slider here on this parameter 454, I can see that the point is actually pretty much over there, something like that. So that's the curve parameter, or the evaluate curve, right? So that's basically it, right? And then, so anyways, that's it. And if you plug into this this little block right here, if you plug in, for example, the other curve, like this one, you'll get a different curve domain. This means that this curve is probably shorter, and it has a different domain. It basically fails at a different point. So each curve, depending on its length, its curvature, will have its own domain. So domain, it's sort of like the length of the curve, right? But so that's one thing. So the second thing on that is that you can get, for example, you can do what's called reparameterize a curve. So you've probably seen this on our companion book, Foundations, a Grasshopper Primer by ModeLab. And you've probably seen that if you right-click here on the curve input and activate the reparameterize option, you'll basically get reparameterize. You will basically assign a new domain to the curve. And it's important to note that this happens without changing its geometry. It's a little bit difficult to understand, but basically it's as though, for example, on the other curve, let's go back a little bit here and let's plug in the first one that we had. And if you remember that when you're here at 0, this is t equals 0. So this is parameter t equals 0. And then I think we had number 5 here. So let's do 5. So that'll give you, oh, sorry, this is without the reparametrized curve. So this will be t equals 5, and that's over here. And that's without the reparametrization. So now, if I grab, I'm gonna reparametrize the curve, and I'm gonna get a 0 to 1 slider, right? So I'm gonna plug that in here, and then just delete that, and now you can see that that same point here is at 0.13. And that is because the curve is being reparametrized when it's going into the input of that component. And what reparametrize means, it's that it's assigning a new domain to the curve, and that domain will go from 0 to 1. What that means is that if I look at the entirety of the curve, if I look at the whole curve, like this curve here, you basically, when you reparametrize a curve, the start point of the curve will be t equals 0, and the end point of the curve will be t equals 1. Okay? And then everything in between will be just a floating point number, a decimal number. In this case here, you will have 0.14. And then if you go to the midpoint will be, you guessed it, 0.5. So this will be 0.5. And then somewhere around that, for example, that would be 0.75, for example, which is roughly 3/4 of the curve. You can think of it, you can see that it moved over there. So you can think of a reparametrized curve as a curve that has a new domain from 0 to 1. It's sort of like a percentage or a fraction of the curve. Basically, the whole curve will go from 0 to 1. And that can happen basically in several curves. You can see that I don't need to know how long the curve is to know that at 0.5 of the reparametrized curve, you basically get the curve midpoint, and then at 0 you get the curve start point, and then at 1 you get the curve end point. Okay? So that's what you get from the evaluate curve. That's the curve domain and the curve parameter. Those are the concepts that are important for this part of the video, where we're looking at curve parameters and reparametrizing curves. Okay? So in the next part of the video, we're going to look at how to use this same concept, but in surfaces. Okay, so if we have a surface, like I said on the introduction to this topic, and you can think of surfaces as arrays of 3D curves that are arranged in 2 directions. So you can think of this surface as this curve, and this curve will be translated along this other curve. That was a lousy drawing, so let's redraw that. So this curve will be sort of translated along this other curve. So that means that at every point on this directrix curve, you will have the same curve. Okay? So what that means, for example, is you can just think of that surface. You can think of this surface as basically, you could, for example, you could divide this surface and then getting the start point of this curve, and then, sorry, the start point of that curve, and then creating a vector from that start point, which will be this one, to every one of these points. This divide curve component will give you. So then that's a vector. And what you could do is you can just translate or move that first curve, which will be this one, using these vectors as a motion vector. There you go. So you can think of this translation surface as a directrix. This is the directrix. Let me just write that down for you. Directrix. And that directrix will be translated along the generatrix. So this is the generatrix. I'm sorry if I can't pronounce that correctly in English, but that will be your generatrix. Okay? So basically, if you have, for example, this count goes, I don't know, let's do 100. You basically have 100 of these along 100 points along the red curve, the generatrix curve. So that's how you construct basically a translation surface, and that's how the surface works. Okay, so you can think of each one of these points. Well, it's along the curve, the generatrix curve. So let's just say that if it's 100 points and the curve is reparametrized, like we saw, this will be parameter t equals 0.01. This will be parameter t equals 0.02, etc., etc., etc. So you have a bunch of curves along other curves, and that's how you construct surfaces in Grasshopper. That's what's going on in here as well. So for example, let's do this again, but let's use evaluate surface. So let's evaluate this surface. Let's reparameterize it. And then let's go with a slider and set that slider to 0.5. And we have the midpoint of the curve, right? So what we're going to do now is let's do that same thing, but with the other curve, which is right here. There we go. Okay, so now if we put a copy of this curve on this point, and if we put a copy of this curve on this point, we will get sort of the midpoint of the surface. So let's try and do that. For example, let's do vector. Well, let's find the endpoints of both curves first. So let's get, for example, these are the endpoints and this is the start. So let's get a vector from this start to whichever, for example, this one. So that will be this vector, right? So that's that vector. So let's do that. So let's get that vector. And what I'm going to do now is translate or move this curve to that point. So there it is, right? There it is. So again, just remember this is at t equals 0.5. So now let's do the same, but with the other ones. So let's get a copy of this, and then let's do this, and then let's do this, and then we get that, and then we're gonna do the other curve, which is here. Okay, so what I'm doing here is I'm moving the other curve, this curve, I'm moving it with this vector, right? And this vector here is, well, that point there is at t 0.5. All right, so it's all fine, it's all good. Both of these surfaces are at lie on, both of these curves, sorry, lie on the surface. right? So you can say that this point right here is exactly at half of one direction here, and then exactly at half of the other direction. So this point right here is at 0.5, comma 0.5. So that's what's going on. And that's a way of understanding surface domains. You can think surface domains. That's a way of understanding surface domain as just the length along curves in both directions of a surface. And at any point in the surface or on the surface, you will have a curve on one direction and a curve on the other direction. And that point will normally have 2 coordinates. So that's one way of understanding it, but that's not very helpful right now. That's just a little bit complicated. However, we can look at it with analysis tools and then go to evaluate surface. And if we evaluate the surface, it's the same thing. It's very similar to evaluate curve, but here in evaluate curve, we had just one number, which is what, like, we had one number going into the parameter, the t parameter. But here it asks us for a point, and if we hover the cursor, it's a UV coordinate. And I'll get to that in a minute. So let's just, for example, go to vector, point, construct point. And then let's just connect that there. So you can see that we have now, this component is now working, and it's giving us a bunch of things. It's giving us the actual point, which is this little cross right here. It's giving us a normal direction, which will be the normal vector. It's giving us a frame, which is the tangent frame to the surface at that point. So let's see, for example, if we change these coordinates, let's change this, let's just grab a slider and then change this to the, for example, this is the one coordinate. Remember that we had t equals 5. Let's just go to 100 over here. And let's just go to 5 here. So remember that we have t equals 5 here. So that what that means is that on the surface, we're moving 5 units here. So that will be u equals 5, because when it surfaces, instead of x comma y, it will use u comma v, which is 2-dimensional coordinates mapped to a surface. So along or on the surface. Okay? So if we do, for example, curve, evaluate curve on this one, and then we get that same parameter, we get that same exact point. The difference with this one is that we can actually get another slider, and we can get that, we're gonna get that point over here. So what that means is that this point is walking 5 units on this direction, and it's also walking 5 units on this direction. Okay? So the UV coordinate, of that point is actually 5, 5. But if we look at the absolute or world coordinates of that point, that'll be different numbers. It'll be close to 5, 5 because the origin of the surface is at 0, 0. But sorry, it'll be close, but it won't be, as you can see, it's not 5, 5. It's different because these coordinates are mapped to the surface. So UV coordinates are mapped to the surface. Okay? And that's one way of understanding surface domains. As we saw with the curve domain, you can reparameterize a surface. And what that will do is that it will clamp, or it will change the surface domain to make it go from 0 to 1 in one direction and from 0 to 1 in the other direction. So this is actually not working anymore. But if we change the values here to go back to 1, you'll see that here, for example, we have that point over here, and then that'll go over here. So again, if I go 0.5 here, oh, sorry. So that will give me a pretty cool, just that's the point right there, which coincides with t equals 0.5, and then t equals 0.5, and this point will be u comma v 0.5 comma 0.5. So that's what that is, basically. That's what that is. Another way of understanding these curves, this is pretty easy to understand in translation surfaces. But when you're using transition surfaces like lofts, which they don't normally correspond with those directions, sometimes the surface will be a little bit more complex. So you can also use, for example, you can use curve, spline, isocurve. So an isocurve will take a UV point. Let's just put that as 0.5 comma 0.5, like you see right here. Go enter, and then let's reparameterize. So these isocurves, you can see that it's giving us this U and V isocurves. You can also get that UV point using a bidimensional slider, which is this one right here, MD slider. And you can see that it's changing quite a bit like that. And what an isocurve is, it's basically a curve that's along a surface, and it has the same U parameters all along that curve. And what changes is the V parameters. So that'll be your U isocurve, and the V isocurve will be the other one on the other direction. Okay? So, and this is true for any type of surface, even if it's a flat surface like this one. This is basically the same thing. You're getting the isocurves. For example, here, let's just say that this is 0.77, like you see here. And then this distance will be 0.33 when compared to 1 to 1. If this is not reparametrized, if the surface is not reparametrized, you get that sort of in absolute units. But you can also change that to be something different. But anyways, so that's another way of understanding surfaces in Rhino. Surfaces in Rhino can be thought, or in Rhino and Grasshopper can be thought of as sort of flexible, like flexible material surfaces that start out flat like this, but then you sort of deform them, but their properties sort of, they're sort of the same, so something like that. Another example is sort of like a flat sheet of paper. So I'm gonna sort of change my camera. So another way is think of a flat sheet of paper like this one. So what I'm gonna do is I'm going to create a point at exactly half of that surface. So let's just say that this is 0.5 of the length of the surface, and then you will have 0.5 of the width of the surface, like this. Okay, so we have that. So now just think of that as a starting point for our surface, just sort of like we had on the Grasshopper definition of flat surface. So now, and this point, it has its own coordinates, like absolute coordinates. So now think that we sort of crumple and deform that surface. Well, if you're a little insect, like a microscopic insect, and you want to get from this point in the corner of the surface to that point that's exactly at half of the width and half of the length of the surface, and you can only walk along the paper of this sheet of paper, you will actually walk the same amount if the paper was flat or if it's all crumpled up. And that's sort of the analogy to understand NURBS surfaces. NURBS surfaces are these objects that allow us to sort of deform, you can sort of deform them using control points and different tools, but they will always have this sort of domain, and they will always have isocurves. They will always have u and v directions, and you can always find any point along the surface just by using two coordinates that can be a reparametrized version of the coordinates. So anyways, I hope that wasn't too complex. It's just an introduction. This part is not very it's an important part of understanding and using surfaces. And what we're going to do now is we're going to create arrays of these points in a surface. For example, you can go to surface, and you can go to utilities, and you can go to divide surface. So what this will do is you can divide a surface in the same way that you can divide a curve. You can divide a surface in segments, but you need to provide division numbers for both the u. For example, this will be 5, and you can see that you have 1, 2, 3, 4, 5 divisions, and you can have, for example, I don't know, let's say 100 divisions on the other side. So you can change that as well. So you can do divide surface as well. And what you get is you get points on the surface, but you also get the normals and the parameters on that surface. So you have a bunch of things. Let's just go with 20 here, and then let's just go with 20 over here as well. So there you can have a grid of points. And what's cool about this kind of way of understanding, you can see that, for example, I don't know, let's just say that, or let's go back to 10 and 10. And right now the surface is not reparametrized, but this isn't very important. If it was, this point will be, this point would be, this point right here would be 0, 0.1, because this direction is divided into 10. And this point would be this would be 0.1, 0. And this would be 0.1, 0, 0.1, this point right here. And this point right here would be 0.1, comma 0.1. Let's look at it. If we look at it with this component here, if we put this on 0.1, comma 0.1, that's what we get, right? And then this will be 0.2, comma 0.1, 0.3, comma 0.1, 0.4, comma 0.1. Yeah, you can just get all of those. This is 0.1, comma 0.1, and then this one is 0.2, comma 0.1, and then this will be 0.3, comma 0.1, and you can sort of get that. You can see that all the points here will have that 0.1 as their v parameter, and you're increasing the u parameter. And that's the same for curves on the other side. You will have 0.1, comma 0.1, and then you will have 0.1, comma 0.2, etc., etc. So those are UV coordinates and how to get points on surfaces. So I hope that this is clear enough. We'll put this to work in order to make a surface panelization. That's what we're going to do on this topic. A surface panelization. And the surface panelization, what that is take a surface and discretize it into different parts in order to make it either buildable or more manageable, or etc., etc. So we'll get to that in the next video. Thank you for watching, and that's it for this video. Goodbye.